Alright, hi everybody. So we are in the last section of chapter 6. So we're going to look at one more method of integration that's going to help us solve a lot more integrals. So this is integration by substitution. This is also called the U-substitution method. This substitution method is how we're going to work with the chain rule. So oftentimes when we have functions that are a little more complicated, they're composite functions, right? They have functions inside of other functions. We can take their derivatives using the chain rule, but their antiderivative is not as clear cut. So we have to develop kind of a process to be able to take these antiderivatives. So first off, we're just going to start to look at this relationship a little bit. So use the chain rule to find f prime of x, and then write the corresponding anti-differentiation formula. So, like for this first one, we have f of x equals e to the x squared. So, f prime of x, the derivative of this is going to be, again, e to the x squared times the derivative of that inside function, right? Times the derivative of x squared, so that's going to be 2x e to the x squared. So, if we're talking about anti-differentiation, so again, if 2x e to the x squared is the derivative of e to the x squared, then e to the x squared is the antiderivative of 2x e to the x squared. Okay, so we can write that using our integral notation. So, integral of 2x e to the x squared dx equals e to the x squared plus c, of course, that arbitrary constant. Okay, now let's look at the next one. So f of x equals 1/6 times x squared plus 1 to the 6th power. So let's take the derivative of that. Okay, so f prime of x and that's going to be, so do the power rule, so I'm going to bring the 6 down. It's going to cancel with the 1/6. So we're just going to be left with x squared plus 1 to the 5th times the derivative of the inside function. The derivative of x squared plus 1 is 2x. So that would be our derivative. So writing the antiderivative, we have antiderivative of x squared plus 1 to the 5th times 2x dx equals that original function, 1/6 x squared plus 1 to the 6th plus c. Okay. So, let's look at one more. Take the derivative of the natural log function. That gives us, right, 1 over the inside, so 1 over x squared plus 4 times the derivative of the inside, which again is 2x. It won't always be 2x. That's just kind of what we're dealing with for these first few examples here, just to get the hang of it, since we're more comfortable with the x squared and 2x relationship. So then the antiderivative of 2x over x squared plus 4 dx is ln of x squared plus 4 plus c. Okay, so when it comes to taking antiderivatives of functions like this, hopefully you're starting to pick up on a little pattern here that in all of these integrals that we're working with here, they all have the original function, right, or that derivative function, and then it's being multiplied by the derivative of the inside. Okay, so it's got that right there, it's got that right there. In these cases, it happens to be 2x all the time, but that won't always be the case. So we need to start identifying where our inner function is and where our outer function is, just like we did with the chain rule. So when we do the substitution, we can identify where that inner function is and where its derivative is. And that's going to help us take these integrals. So to make a substitution, let u be the inside function and du is going to be u prime of x dx. Okay, or if you want to write it as in the Leibniz notation, that would be du dx dx. Okay. So, but essentially when we're making a substitution, we want to identify the inside function. When we say inside function, we're talking about kind of these guys up here, right? So whatever was on the inside. And then by default, the du value is just the derivative of whatever function we picked. And the reason that's going to be important is because when we're taking these integrals, here we have inside function, here we have its derivative, here we have inside function and its derivative, right? So these pieces are going to be substituted, and that's going to make it a lot simpler for us to integrate. Okay. So let's go ahead and make a substitution for these. So we've already seen how to do these from the derivatives, but let's show how to do it using the u substitution. So in this case, identify the inside function as the x squared. So we're going to let u equal x squared. Then du, so du we don't have a choice. It's just whatever the derivative of u is. So that's going to be 2x dx. Now when it comes to making the substitutions, we need to make sure that we cover all of the x's appropriately. Make sure we can replace them all with u values. So the x squared covers that one, and 2x dx covers that, and we're good to go. So let's go ahead and make the substitution. So this is going to be e to the u du. All right, so does everybody see how we're making that substitution there? Because now I can integrate this expression using just my knowledge of integrals. So this is just the antiderivative of e to the u is just e to the u plus c. And now we go back and we say, okay, well, but now I know what u is, right? That was my x squared. So I'll go ahead and sub back in for x. Put my final answer in terms of x. And we get exactly what we got before. Okay, so doing these u substitution, we identify inside function and its derivative. Switch everything from x's to u's. Then take the simpler integral. Once you have the integral done, you can now switch back from the u's back to the x's again. Okay, so let's look at the next one here. So identify inside function. So this is going to be let u equal x squared plus 1. So, and again, we're choosing the u value, but the du value, we have no choice. It just depends on what we picked. So in this case, it's 2x dx, just like it was before. So, and if we match up, so the u is going to replace the x squared plus 1, so that's right there. And the du is going to replace 2x dx, so that's going to be there and there. So and they don't have to be consecutive in the integral, because you can move them around if you want. But now we've gotten rid of all of the x's. So this leaves us with u to the 5th du, okay, which is an integral that we can compute just by undoing the power rule. So this is going to be 1/6 u to the 6th plus c. And now we can go ahead and sub back, because I know that u is x squared plus 1. So this is just going to be 1/6 x squared plus 1 to the 6th plus c. Okay, which is exactly what we needed to get here. Okay, and then the last one. So the fractions can be a little harder to identify inside versus outside function, but just when you're looking at it, just notice that the derivative of x squared plus 4 is 2x, so that might be a good indicator of which one is which. So, and if you pick the wrong u value, that's okay. It may not work out, but then just go back and try a different one. Okay, so there is a bit of trial and error in this process. So let u equal x squared plus 4. And du is 2x dx. Right, so notice if I had picked it the other way, I would not have gotten the result I needed. So this way worked out for us. So the 2x dx is going to get covered by the du, and the x squared plus 4 is going to get covered by the u. So this gives us integral of 1 over u du, which the antiderivative of 1 over u is ln of absolute value of u plus c. Okay. And now when we sub back in, x squared plus 4 is always positive, so we don't need the absolute value on it. You can leave it on though if you want. That's not a problem. And that would be it. Okay. So one important thing to take note of, in order for this process to work, the derivative function has to be there. Because if the derivative, like in these examples, the 2x, if we didn't have the 2x there, we couldn't have made these substitutions. Because if you don't have it all exclusively in terms of u, if there's some x's and u's getting mixed around together, we can't integrate that. Okay, it has to be one variable only when we're doing the integration. Okay, so let's look at some more examples here. So find the integral of t e to the t squared plus 1. So we need to identify the u value so that we can get our du value. So I would say it looks like that function inside of the power on the e looks like a good candidate for the u value. And if we're wrong, we can always go back and try again. So let's take a shot at this one. So let's let u equal t squared plus 1. Then du is 2t dt. Okay, so let's see what we got here. I got t squared plus 1. That's going to cover my power. And then I've got t dt is this right here. But notice we have here an extra factor of 2 in this du expression. This doesn't match up exactly, so we can't do the substitution exactly like this. But what we can do, in order to make this match perfectly, all I want is the t dt. So if I just move this to the other side, that's going to give us an appropriate substitution. Okay, so all we need to do is divide both sides of this by 2. So I get 1/2 du equals t dt. Okay, and now, if we look at the substitution, t dt gets substituted for perfectly with the expression 1/2 du. So the bottom line here is that these derivatives, these expressions, can be off by a constant. Okay, in this case it was multiplied by 2, but there was no 2 up here in the integrand, so we needed to go ahead and get rid of the 2. And we did that by just dividing it away. So now when we do the substitution, this is going to be the integral of e to the u. And then instead of just du, now it's 1/2 du. That gives us our match, right, for our substitution. So 1/2 du. And then the 1/2 is just a constant, so it can just get pulled all the way out of the integral. And now we're just left with e to the u du inside. Take the antiderivative of that. So that's, again, just e to the u plus c. Sub back in what we know for u. So this is going to be 1/2 e to the t squared plus 1 plus c. So that's going to be our expression. So again, we can be off by a constant and just divide it away, and that's going to be okay. If we had extra factors of t in here, there's no way that we could do that. Okay, but it works for a constant. Okay, so let's look at one more that utilizes the same kind of thought process. So identifying inside versus outside, so this one's inside the square root, so I'm going to pick that, but also notice the derivative of x to the 4th will give me a cube, so that seems like a good choice. So let u equal x to the 4th plus 5, then du equals 4x cubed dx. Now again, if we look at how this matches up, that covers that, and x cubed dx is right there. But it has an extra multiple of 4 that we don't need, so we're going to divide the 4 away. So we get 1/4 du equals x cubed dx, and now that's going to match perfectly with our integrand. So now let's go ahead and do the substitution. So this is integral of square root of u times 1/4 du. Go ahead and pull out that 1/4. So now it's just a matter of using the previous integration techniques that we've seen. So pull out the 1/4 integral, that's u to the 1/2. Right, that's the square root. So we get 1/4 times antiderivative of u to the 1/2 is going to be 2/3 u to the 3/2 plus c. Simplify that fraction. There's a 2, there's a 2. That's going to be 1/6 u to the 3/2. So u is x to the 4th plus 5. So that's going to be x to the 4th plus 5 to the 3/2. Plus c. Okay. So we are able to get there because, again, we had the inside function and its derivative both showing up in the integrand. Now there's a brief note it makes down here, just a word of caution, because if we had had the integral with x squared in it instead of x cubed, we would still have the same u value, same du value, but we would only have an x squared in the integrand, and we would somehow have to get rid of an extra factor of x, because we'd have x cubed instead of x squared, and that actually wouldn't work. We wouldn't be able to apply the same method doing it that way, so we just have to be careful that we make sure to cover all of the x's with u's. Okay, let's look at one more. So we have e to the cosine of theta, sine theta, d theta. So in this case, we have, it seems like two choices, right? We could pick the cosine, could pick the sine to be the u value. You might be inclined to pick the sine because you know the derivative of sine is cosine. The problem with that is if you let u be sine, then du is cosine theta d theta, but cosine is up in the power of the e. So that's not going to work out the same way. So we do need to pick the cosine to be the u value, because otherwise you're going to get, right, integral of e times u, and then somehow your d theta and your cosine theta up here, this and this are going to have to become du, and that's not going to work because they're not on the same level. One's in a power and one's not. Okay, so we just have to be careful with those choices there. But in this case, we do need to use the cosine theta for our u value. Then du is negative sine theta d theta. So it almost matches, right? Except this one has a factor of -1 in it that our original doesn't. So just divide it away or multiply, whatever you want to do. So just negative du equals sine of theta d theta. And let's again always check to make sure it matches perfectly. So cosine theta, that's good. And sine theta d theta right there. Perfect. So this is going to be integral e to the u times -1 du. Okay, you can pull the negative all the way out. Take the antiderivative. Right, so that's going to be negative e to the u plus c, which is negative e to the cosine of theta plus c. And that's it. Okay, and then just like all these other integrals we've looked at, if you ever want to just check and verify that you did it correctly, just take the derivative of your result and you should find that it gets you back to your original again. Okay, that's always a good way to check your work on the integrals and make sure that you did it correctly. Okay. Now, the last thing, so up until this point we've only been dealing with indefinite integrals, so we haven't talked about how we change bounds, right? How do we deal with definite integrals that give us a specific interval? So we have two methods of dealing with these integrals. So the first is you can first basically do what we've been doing. Find the antiderivative first and evaluate it all in terms of u, then plug back in the x and go back and evaluate it using those bounds. Okay, so you go through the whole u substitution, you switch back at the end, and then plug in the bounds. Or you can actually change the bounds with the substitution. Use the substitution to change the bounds, and then you don't have to go back to x anymore. Okay, so we're going to do that on this example, and I think I fixed this on yours, but I haven't yet on mine. So this should have bounds on it. So this should be the integral from 0 to 2. So 0 and 2. There we go. Okay, or actually, because I posted this a while ago, so yeah, you just need to add those in there. So integral from 0 to 2. So the u substitution that we make is going to be the same no matter which method we use. So let's go ahead and set that up right now. So we're going to let u be x squared, then du equals 2x dx. Notice there is no 2 in the integrand, so we do need to get rid of it. So we get 1/2 du equals x dx. Okay, so that's going to be used in both methods. So let me do these in different colors here. So solution 1. So our first method is we just solve the corresponding indefinite integral. So integral x e to the x squared dx. Solve that first. Okay, so that's going to give us 1/2 e to the u du using the substitution, right? The substitution up here, which is going to give us 1/2 e to the u plus c. Okay, and then sub back in, so 1/2 e to the x squared plus c. Once we get this antiderivative, now we go back, so we can say thus the integral from 0 to 2 of x e to the x squared dx is 1/2 e to the x squared evaluated from 0 to 2. You don't need to include the plus c because you never do on a definite integral, but you can if you want. So this gives us 1/2 e to the 2 squared, so e to the 4 minus e to the 0 squared, so e to the 0. So we get 1/2 e to the 4th minus 1, because that's what e to the 0 is. Okay, so that's method 1. So you just go about your business, right? Do exactly what we've been doing before. Take the general antiderivative, sub back in for x, and then once you've done that, then go back in with those original bounds and go ahead and evaluate it. Okay. So the other method that we have, oops, wrong tool, there we go. For solution 2, so in this case, we're going to convert the bounds from x to u using our substitution. So when x equals 0, u equals, so let's go back up to the substitution here. U is just x squared, right? We have that right here. U is x squared. So when x is 0, u is 0 squared, which is 0. Okay, and then when x equals 2, u equals 2 squared, which is, of course, 4. So now what we can do is set up the integral using only u and only the new bounds that we created. So thus, we have the integral from 0 to 2 of x e to the x squared dx equals the integral from 0 to 4 of 1/2 e to the u du. Take the antiderivative, so that's 1/2 e to the u evaluated from 0 to 4. So we get 1/2 e to the 4 minus e to the 0, which of course gives us 1/2 e to the 4th minus 1. So we end up getting the exact same answer as we did before using the converted bounds. So which of these methods you use to solve definite integrals by substitution is totally up to you. I don't have a preference either way, so sometimes it can depend on the problem, but a lot of times it's preference. So pros and cons to each. Some people like the first method more because it allows you to just do the work the way we had done it before and not have to convert the bounds, because some people find converting the bounds is a little more confusing for them. So that's fine. You can do it that way. Some people prefer the second way of doing it because they like being able to not go back to x, and they feel like it's a bit shorter to do it that way, okay, and not have to worry about subbing back and all that kind of stuff. So it's totally up to you which method you prefer to use. But that's it. So that's the end of 6.6, and that's the end of Chapter 6, so our discussion on integration. So that's going to be it for this kind of unit for examinable content, okay, on Chapters 5 and 6. Chapter 8, which we're going to start in a couple of weeks, will bring in some brand new topics. So that's it for our integration stuff, and I will talk with you all very soon.